Mostly we're gonna spend most of the time talking about matrix calculations because those are going to be important in this class. Before that, I want to talk about some simplifying assumptions. So all of the things that we're doing in this class are based on simplifications. You couldn't use like the true laws of physics to derive all this stuff. It would get too complicated. So you have to make simplifications. And any simplifications require assumptions to be made. And so this class, pretty much through this whole class, there are 4 simplifying assumptions that are going to be underlying everything. So I want to bring those up now, and I'll bring them up later. These are things that you should remember, have in mind all the time, like they're worth memorizing. So think about statics for a second. Like, so these simplifying assumptions involve material properties. They also involve a little bit about loading, the kind of loading that's allowed. What type of materials did our calculations in statics hold for? Rigid. Really, I guess, as long as the geometry that was drawn was the final geometry, you didn't even have to assume that they were rigid. You didn't have to assume that there was anything uniform about them. All of those things that we talked about in statics would hold for cardboard, they'd hold for steel, they hold for everything. But that's not going to be the case in deform, where how the material bends is going to be a significant part of the calculations we do. Okay, so that's like a fundamental difference between deform and statics and dynamics. So here are the simplifying assumptions that we're going to make. The first one is we're going to assume that all of the deformations we're talking about are small deformations. So that means, say that you have an object like this, and you apply forces this way, and the effect is that it compresses like this, okay? A deformation like this is okay. A deformation that's like just a few percent of the size of the object. But something like this, is not okay. The math that we're using would give really bad approximations for big deformations like that. So what's the cutoff? You can think of a handful of percent of the original length as being a reasonable cutoff. For the most part, we're not going to get anywhere near those, like a few percent. We're going to be talking about point something percent and 0.0 something percent as a deformation. But you can think of it as sort of just a limiting thing. These results are better the closer it is to 0 deformation, okay? And they're worse as the deformation gets bigger. By the way, the bigger effects come in when you have changes in angle, when orientations start to change. Okay, the second assumption is we're going to assume that all the materials that we're dealing with have a linear relationship between stress and strain. We haven't talked about what stress and strain are yet. But you've dealt with something that you assume has a linear relationship between stress and strain. That's Hooke's law, okay? And we're going to deal with a three-dimensional version of Hooke's law that where instead of a constant k, instead of just a scalar constant of proportionality, we're going to have a matrix of proportionality. But even in 3D, people call this Hooke's law. So all the materials have to obey Hooke's law. So an example of something that doesn't do this is rubber. Okay, so we wouldn't get very good results for a rubber ball. Okay, this works pretty well for engineering materials, metals, up to a certain point. And we'll talk more about what that point is. The third restriction is the materials have to be homogeneous. Anybody know what that means? Yes, exactly. Yep. So it has to be the same material throughout. I don't actually know what they do when they homogenize milk, but I would imagine that they take out pockets of stuff, you know, and make it all like sort of uniform the whole way through. Take out, like, I assume that before you homogenize it, there's like little blobs of goop, and you take out the blobs of goop, and then the milk is the same everywhere, you know? And it breaks it up. Okay, yeah. And so it's the same idea. So we could deal with homogenized milk in this class, but not pre-homogenized milk. And the last one is isotropic. Materials have to be isotropic. Anybody have any guess what that means? An isotropic material has the same properties in every direction. This is true of most engineering materials. It's not true of things that, say, would be really able to resist compression in one direction but compress really easily in the other direction. That would be a material that's not isotropic. So really wood is not isotropic. Bones, yeah, that's a really good example. Long bones, like some bones are pretty isotropic, but like your femur is designed to be very strong along the long axis, but doesn't usually have to deal with, you know, resisting compression side to side, and so it's not very strong that way. And so you have to be careful applying the techniques that we're going to do to wood or like a long bone. Whereas a bone like the pelvis that deals with forces in a lot of different directions is more isotropic. Any questions about those simplifying assumptions? So essentially what this means is overall, these hold for most engineering materials like steel, concrete, when these engineering materials are in the most common engineering applications. And notice that most of these, let's see, 1, 2, 3 of these 4 properties are purely material properties. So numbers 2, 3, and 4, they either hold for steel or something or they don't, okay? The first one, and actually a little bit of the second one, and I'll go into that later, has to do with how you're using the material. So do these 4 all hold for steel? Well, the first one, if you apply enough force, you could squish a cube of steel flat as a pancake, and then the first one wouldn't hold, you know? And so it depends on the material and it depends on how you're using it. Any questions about any of those? Okay. So mathematically, before we get started, I want to talk about matrix calculations because matrices are going to be a big part of this class. So let's say that we have a matrix A, and let's say it's equal to 2, 1, -2, 4, 0, 6. Okay. So this matrix is called a 3 by 2 matrix. The first index refers to the number of rows, and the second index refers to the number of columns. And inside the matrix, you can refer to the different elements of the matrix by listing first the row number and then the column number. So for this matrix, capital A, element A11 is equal to 2. Element A12 is equal to 1. Element A21 is equal to -2. Element A22 is equal to 4, and so on. Okay. So that's how you refer to those elements. In this class, there are going to be 4 main matrix dimensions that we're going to use. So we'll have 4 common sizes. The first one is 3 by 3. And that is the form of the stress tensor. So the stress at any point in a material is going to be given by a 3 by 3 matrix. An example is, that's the Greek letter sigma. That's usually what people use to represent the stress. And an example might be 5 times 10 to the positive 6 pascals, 0, -2.5 times 10 to the 6. Then on the main diagonal, -1.5 times 10 to the 7, and 8.0 times 10 to the 8. And then 0, 0, 0, -2.5 times 10 to the 6. And one thing about stress tensors is they're always symmetric matrices. And I'll talk about what that means mathematically, but you can see that the element sigma 3, 1 is the same as the element sigma 1, 3. Okay, and that's true anytime you interchange those indices for a stress tensor. Okay. The second size that we're going to see pretty often is a 3 by 1 matrix. A 3 by 1 matrix is a vector in three-dimensional space. So for example, the vector V is equal to 10,000 newtons, negative 45,000 newtons, 5,000 newtons. So just like in statics, external forces or external couples are going to be vectors, and so we'll represent them as 3 by 1 matrices like this. The third type is 6 by 1. And this is how we'll represent the strain at a point. And it's also how we'll represent what's called the Voigt form of the stress. Oops, like John Voigt. I think that's who it's named after, but I'm not sure. Okay, so for example, the strain at a point is represented by epsilon, and you might have a value of negative 1.5 times 10 to the minus 6, 6.0 times 10 to the minus 7, 0, 0, 5.5 times 10 to the minus 6, 0. That's right, for the vector, yeah. I'll have to go into that a little bit, but yeah, it's it'll make more sense once we talk about tensors, what a tensor is. And then the last type that we're going to see pretty often is 6 by 6. That is the form of the stiffness matrix and also the compliance matrix. Those are two different matrices, and each one is one way of representing material properties. And the way it works is the strain in its Voigt form is equal to the compliance matrix times the stress in its Voigt form. Okay, and the stiffness, it just works the other way. The Voigt stress is equal to the stiffness matrix times the Voigt strain. And these are matrix representations of Hooke's law. So you can think of the stiffness and the compliance matrix as equivalents to like the spring constant, okay? Except that they're a matrix thing that has 36 entries instead of a single value, okay? For any matrix A, there's a transpose called A with T up like an exponent. And to get the transpose, just interchange each row number with the column number. So, for example, if you have this matrix A that's equal to 1, 2, 3, 4, 5, 6, okay, the elements are A11 is 1, A12 is 2, A21 is 3, A22 is 4, A31 is 5, and A13 is 6. Well, to get the transpose, let's call the transpose a new matrix B, so that's equal to A transpose. That's going to have the values A11, interchange the 1 and the 1, and you get 1 back. Yep, I did those wrong, didn't I? Thanks. So 3, 1, and 1, 3. Okay, so if you interchange these, you still get A11, right? So
It's supposed to be A32 or that last.
oh yeah. A sorry. 3, 2. Thank you. Okay, so A11 is equal to 1. Now instead of A12 being equal to 2, A21 is going to be equal to 2. Okay, so let's write it over here. Instead of A21 being equal to 3, A12 is going to be equal to 3. Instead of A31 being equal to 5, A13 is equal to 5. Instead of A22 being equal to 4, well, interchanging those doesn't change the indices, so on the diagonal you still have 4. And then instead of A32 being equal to 6, A23 is equal to 6. And so you end up with this matrix 1, 3, 5, 2, 4, 6. This function is built into TI-89 calculators and probably some of the older ones. So let me just say how to enter matrices into your calculator. Make sure you know how to do that. In TI calculators, you'd enter a matrix as, so you do square bracket, and then you'd enter 1, comma, 2. So that would give you the first row. I'm doing this matrix A. And then you'd go semicolon. That's how it knows to go down to the next row. So then you'd enter 3, comma, 4, semicolon. And then you'd enter 5, comma, 6, square bracket. And if you wanted to put this into a variable, you'd use the STO function. I think it shows up as like an arrow. Type in the A. And that would put this matrix in A. Anyone who has a calculator with them, I guess you might as well take it out and try this. Make sure that you can enter this matrix. And then if you, once you have this matrix in here, if you go to catalog, and once you get into the catalog, just press the letter button T, and I guess transpose would be the first one that comes up if you have it on your calculator. If not, it's easy to program. And so then if you entered like the matrix A that you just filled in with those values, and then click on the transpose program, it'll put that little T up in the corner, and if you hit enter, it'll give you the transpose of that matrix. Okay. I don't remember. Probably some and some not. I don't know. They have all those different versions of the 84. But anybody who wants to come talk to me after class and we'll figure out how to do it. Any questions about that? Now, a type of matrix that is important in engineering is square matrices. And that has the meaning that you would, like if you had to guess what a square matrix is, this means what you think it means. Square matrices are ones where they have the same number of rows as columns. And there are two definitions that I need to give you for square matrices. The first is the diagonal elements. The diagonal elements are the ones, so like for example, if you have a matrix 1, 3, 1, 2, 2, 4, 1, 0, -6, that's a square matrix because it has the same number of rows as columns. And the diagonal elements are 1, 2, -6. Okay. Mathematically, notice that those are all the elements with the row number equal to the column number. Okay. So the 1 here is row 1, column 1, so they're equal. The 2 is row 2, column 2, so they're equal, and the -6 is row 3, column 3. Okay. And something to notice about the diagonal elements is, so notice, the diagonal elements are unchanged by the transpose. You take the transpose, you still have those same diagonal elements. Okay, the second definition that we're going to use for square matrices is a symmetric matrix. And a symmetric matrix is a matrix M where M is equal to M transpose. Okay. So any square matrix whose transpose is equal to itself, that's a symmetric matrix. That works out to look like this. So if you had a matrix 1, 3, -1, and then 5, -4, -3. Okay, so I haven't filled in all the values yet. I just picked these totally at random. Is there any, is there any problem with picking these values at random if we want this to be a symmetric matrix? Well, for these 6 values, notice that I haven't filled in any of the flipped indices yet. So these 6 we can pick, okay? But now if you want it to be symmetric, this one has to be 3, okay? This one has to be -1, and this one has to be -4, okay? So the thing to notice about any symmetric matrix is any symmetric matrix has, well, I should say any symmetric 3x3 matrix, because that's the type we're going to use most, has 6 independent elements. Okay, it has 9 elements, but only 6 of them are independent. The other ones come from the first 6. Yeah. Okay. Any questions about any of those definitions? All right, the next thing we have to talk about is matrix multiplication. You can think of matrix multiplication as a series of dot products of vectors. So if you're multiplying, well, so first of all, a dot product if you are taking the dot product of 2, 1, -2, dotted with -5, 0, 6, you get 2 times -5 plus 1 times 0 plus -2 times 6, and you get a value of -22. Okay, so a dot product gets a scalar output by multiplying two vectors. So to multiply two matrices, each output element let's say each output element M, I, J is the dot product of the left matrix row I and the right matrix column J. Okay, so this will make more sense when I draw it. For example, if you have these two matrices, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you're multiplying it to 10, 11, 12, 13, 14, 15, 16, 17, 18. So, I mean, those are just the arbitrary values I chose for those elements. You're going to come up with an output matrix to get the value of element 1, 1 in the output matrix. You're going to take the dot product of row 1 in this matrix and column 1 in this matrix. So the dot product here would be 1 times 10 plus 2 times 13 plus 3 times 16. Okay, and so you'd get 138, where you get that 138 by taking the dot product of this and this. Okay, now in order to get the element 1, 2 in the output matrix, what are we going to take the dot product of? First row here and the second column. Yep, that's right. And if you do that, you get 171. So that's the dot product of this and this. And I'll just fill out all the values so you know you can make sure that you understand this when you look back at it. The second row is 174, 216, 258. The third is 210, 261, 312. And one thing that I would recommend that you do when you're going through this is make sure that, you know, practice entering these in to your calculator. And if you just So if you put this matrix in a variable called A, put this matrix in a variable called B, and then just on your screen type A times B, it'll give you this output matrix. So it'll do all these calculations for you. One thing that's very important to notice about matrix multiplication is the order of matrix multiplication matters. And you might not expect that because with scalar multiplication, the order doesn't matter. Scalar multiplication is commutative. Matrix multiplication isn't. So in other words, matrix multiplication is not commutative. So for example, 1, 2, 3, 4 times 5, 6, 7, 8 is not equal to 5, 6, 7, 8, 1, 2, 3, 4. Okay. You can multiply more than one matrix for example, you could multiply 1, 2, 3, 4 times 5, 6, 7, 8 times 9, 10, 11, 12 by first multiplying two of them and then multiplying to the next one. And which way do you group them to multiply? That actually doesn't matter. So the order matters, but the way you group these and multiplying them doesn't. So you could do this as 1, 2, 3, 4 times 5, 6, 7, 8, and then multiply the output of that to 9, 10, 11, 12. Or you get the same answer if you do it as 1, 2, 3, 4 times the result of 5, 6, 7, 8 times 9, 10, 11, 12. Question?
Does that mean the first matrix row equal to the second column must be equal to multiplication of matrix?
Yes, that's exactly right. You can't multiply any two matrices. They have to be compatible in the sense that the number of elements in the row of the left matrix has to be the same as the number of elements in the columns of the second one. That's right.
Are we mostly going to be multiplying square matrices?
Multiplying what?
Square matrices?
Mostly, yeah, in this class. Yep. Only. Well, unless you think of a vector as a matrix, and then we'll also be multiplying matrices times vectors. Those are kind of the two operations we'll do. Okay, so far, my examples have only used square matrices, but you can multiply any two matrices where the number of columns on the left matrix equals the number of rows on the right matrix. In that case, the output matrix, the result, will have the same number of rows as the left matrix, and the same number of columns as the right matrix. Okay, so here's an example of how that works. You could have a matrix 1, 2, just a 1 by 2 matrix there, and a matrix 1, 2, 3, 4. Okay, and if you multiply those, you're going to get a matrix that has one row, because the left matrix only has one row, and two columns. Okay, so you'll take the dot product of 1, 2, and 1, 3, and you'll get, what's that, 7? Take them, this will take too long. But you'll get oh no. You'll get, oh yeah, that won't take too long. So 1 times 1 plus 2 times 3, 7. And then 1 times 2 plus 2 times 4 is 10. And you get this. Okay. And so notice, this is the last thing I'll say. You can think of a dot product as a 1 by n matrix. In this case, a 1 by 3 matrix times a 3 by 1 matrix. Any questions? Okay. We'll finish up matrix stuff pretty quickly next time, and then we'll go on to defining the stress tensor.